Welcome to this lecture on the topic of probability fundamentals. During this lecture, we'll start by briefly covering uncertainty, then basic probability theory, statistical inference, independence assumptions, odds-likelihood forms of Bayes, and lastly, briefly discuss the trouble with Bayes. Let's start with uncertainty. So first off, why do we care about uncertainty? Many real-world problems need a way to conclude that something is probably, but not absolutely or necessarily true. For example, some observations, such as symptoms, are usually but not always associated with some cause or some specific disease. This is often true in many applications of expert systems across the field of medicine. Here, we simply define uncertainty as the quality or state of being not clearly known. It's this idea of uncertainty that distinguishes deductive knowledge, for instance what we often see in mathematics, from inductive belief, which is the foundation of most of science. Recall our previous definition of deductive reasoning, which starts with a general rule applied to a specific case to reach a logically certain conclusion. Differently, inductive reasoning looks at specific observations to identify a pattern, which is used to make a probable but ultimately uncertain conclusion. Also, we previously discussed statistical syllogisms as a form of inductive reasoning. Here in this example, we have two propositions that can have varying degrees of certainty associated with them, and these are applied to draw a conclusion that similarly has a degree of uncertainty. Specifically here in our first proposition, it says that 90% of Appalachian Trail shelters have water, which has a probabilistic uncertainty associated with it. And a second proposition, the Rocky Gap is an Appalachian Trail shelter, which is certain, ultimately leads to a conclusion that also has uncertainty. Specifically, it's 90% probable that the Rocky Gap has water. Let's talk about some of the potential sources of uncertainty. First, we'll look at uncertainty of inputs. For example, we could have uncertainty introduced by missing data, having noisy data, or the use of imprecise language. Consider that our natural language is, of course, often ambiguous, and that there can be facts described with terms like sometimes, frequently, and hardly ever. Uncertainty in knowledge might result from combining the views of different experts, there being multiple causes that lead to multiple effects, having an incomplete enumeration of conditions or effect, having an incomplete knowledge of causality in the domain, which might mean that our implications are weakly structured, and then of course there's always probabilistic and stochastic effects, or just uncertainty that comes from randomness itself. Uncertainty in outputs can be the result of using inductive, abductive, or analogical reasoning methods, which are inherently uncertain. Furthermore, the use of default reasoning, even in a deductive fashion, can also lead to uncertainty. Further, having incomplete deductive inference can also lead to uncertainty. In artificial intelligence, when we think about uncertainty, we usually begin by trying to quantify the certainty of the information we have. In this table, two separate research studies were conducted asking subjects to subjectively attempt to quantify the level of certainty implied by the use of these different terms. For example, always, very often, usually, often, generally, and so on. And we can see in these two studies that slightly different sets of scores were obtained. Funnily enough, in this first example, always, only received an average of 99 out of 100 certainty based on the data that was collected from these study participants. In this example, we might imagine that we're trying to take raw text and quantify the certainty of information based on the use of some of these terms. And instead of arbitrarily assigning certainty values ourselves, we're surveying a group of subjects to try and understand how people perceive the certainty behind the use of these different terms. At this point, let's dive into what might be a refresher for many of you as we cover basic probability theory. First off, probability is the language of uncertainty, and it asks, what is the chance that something will occur? Probability can be expressed mathematically as a numerical index with a range between 0 and 1, where 0 represents absolute impossibility and 1 represents absolute certainty. We can of course think of this in terms of percentages from 0 to 100. The notation for writing probabilities often looks something like this, P of x, or the probability of x. So for example, if we have a fair coin, the probability of tossing a heads or the probability of tossing tails are both equal to 0.5. It's also possible you could have a slightly biased coin, in which case you'd have the probability of heads being 0.51 and the probability of tails being 0.49. Just to formally review how this would be illustrated mathematically, the probability of success would be the number of successes divided by the number of possible outcomes, where we can see in this equation on the right that the number of possible outcomes is the sum of successes and failures. And of course, the probability of failure is just the opposite. Notably, when we have two outcomes, the sum of our two probabilities of failure and success should equal 1. Now let's look at probability tables. Here we have an example of weather over 365 days of the year, 200 of which were sunny, 100 cloudy, and 65 rainy. So now we can quantify what is the probability that the weather is sunny, or P of sunny. In this case, we have 200 sunny days out of 365, and this would be our probability of sunny. We can use similar notation to represent what the probabilities of different kinds of weather would be, listed out individually, like you can see here. For now, we're looking at the probability of a single outcome, in this case, what is the weather? But now, let's start to think about the probability of having multiple outcomes at the same time. Here's where we get to the idea of disjoint probability. This is the likelihood that one of two possible events, A or B, will occur. Another way of putting this is the probability that big A equals little a, or the probability that big B equals little b, where this downwards caret indicates the or relationship. Notation generally simplifies this expression to look something like this: the probability that A or B has occurred. To calculate what's called disjoint probability, we use the following equation. The probability of A or B is the probability of A alone plus the probability of B alone minus the probability that A and B are happening at the same time. We need to subtract the probability of both events happening together so that the overlapping parts aren't counted twice. Here's an illustration of this disjoint probability situation. In this illustration, the yellow box represents 100% of the probability. The area of A, or B, that doesn't overlap, each represents the probability of A or B alone, respectively. The unique non-yellow areas would be the probability of A or B. And lastly, the probability of A and B would be represented by the area of A and B's overlap. So in other words, our disjoint probability would be the area of A plus the area of B minus this overlapping spot in the middle. This ensures that the overlapping probability in the center is only counted once. Now let's move on to mutually exclusive events, also known as disjoint events. These are events that have no basic outcomes in common, or equivalently, their intersection is the empty set. This happens when you have a situation like this. The probability of A or B is just the sum of probability of A plus probability of B. In other words, there's no overlap. We can see that here in the same illustration of the probability space, that A and B have no overlapping region. So now we can label these events of A and B as being mutually exclusive events, since they don't ever happen at the same time. Next, we have joint probability. This is the likelihood of two events occurring together at the same time. We can use this annotation as shorthand for the joint probability of P and A. It means the same thing as the probability of A and B happening at the same time. We can obtain this probability by multiplying the probability of A and the probability of B, but only if A and B are independent. Here's another weather example, but now we have two aspects of the weather. In other words, the weather can be either sunny, cloudy, or rainy, and it can either be hot or cold. Each of these table cells represents a unique combination of either weather conditions or the temperature. So for example, there were 150 days where it was both hot and sunny. The values within each of these cells represents the joint probability of that event occurring. In this case, we've measured the joint probability directly from the environment and have not had to calculate them. From this table, we can calculate the probability that the weather is rainy by adding the rainy days when it's either hot or cold together, giving us this probability. We can also do the same for if the temperature is hot, where here we add up 150, 40, and 5, giving us 195 out of 365, or this probability. And lastly, we might ask, what is the probability that it was both hot and rainy? And we can see from this table that the probability is 5 over 365, or this probability. Now we might ask if the weather being rainy and the temperature being hot were independent from one another. We can test this by asking if the product of these probabilities on their own are equal to the joint probability we've observed. In other words, days when it was both rainy and hot. So we examine the product of these two values to give us a probability of 0.095, which is different from 0.014. Therefore, this tells us that these two variables are not independent from one another. Here's an illustration of the joint probability where we're asking what is the overlapping space between A and B. Just as a reminder, we need to be careful when we think about joint probabilities and how we calculate them based on our awareness of whether these variables are independent or not. Now let's talk about conditional probability. Here we have a situation where multiple events occur, and we can express the probability that one of the events will occur given that the other is also assumed to have occurred. First off, with conditional probabilities, we're assuming that events are not mutually exclusive. So in other words, there is some overlap. We can denote conditional probability using this syntax, probability of A given B. We can calculate this as being the number of times that both A and B can occur, divided by the number of times that B can occur. Similarly, we can calculate the probability of B given A as the probability of B and A occurring at the same time, divided by the probability of A. Note that if the probability of B and A was ever 0, in other words they were mutually exclusive, this conditional probability would also be 0. However, note that generally the probability of A given B does not automatically equal the probability of B given A. So looking at the probability of B given A, this can be thought of as the fraction of B outcomes where A also occurs. Let's go back to our illustration of the probability space and remember that our joint probability lies here, or the probability of both A and B occurring. Our conditional probability, A given B, is best visualized by this fraction, which is the joint probability of A and B divided by the probability of B. And our probability of B given A would look like this, where we again start with our joint probability divided now by the probability of A. Now we can clearly see why these aren't always equal. Describing conditional probability is really a stepping stone to getting to something we're going to use a lot here, which is the Bayes rule or theorem. So again, we have our equation of a conditional probability, or a probability of A given B. And of course, the similar equation below for the probability of B given A. Notably, we also know that the joint probability B and A is always going to be equal to the joint probability A and B. The order of the variable doesn't really matter here. Therefore, we get this equivalent equation for each. This allows us to substitute in this expression for this one. And this gives us the Bayes rule. Here, the Bayes rule is describing a conditional probability, or the probability of A given B. In terms of the conditional probability of B given A, the probability of A, and the probability of B. So now we have a way to describe conditional probabilities without requiring joint probabilities. We'll see later on why this is a very useful simplification. Also notably, this formula is used extensively to support probabilistic, or in other words, inductive reasoning. Next, we might ask, how do we generalize conditional probabilities to some arbitrary number of events? So far, we've only been dealing with 2 at a time. This is where the chain rule comes into play. The chain rule relates the joint probabilities of events to conditional probabilities. Or in other words, if we want to know the joint probability of A, B, and C all together at the same time, we can calculate this as the probability of A given B and C times the probability of B given C times the probability of C alone. This specific example can be further generalized as such, where instead of A, B, and C, we're using A1, A2, all the way up to AN to represent that there could be any number of events involved in which we're interested in their probabilities. So in this calculation, we can see the same kind of equation elements we had above, just that their order is reversed here. So now we have the probability of A1 alone, corresponding to the probability of C alone, the probability of A2 given A1, corresponding to the probability of B given C, and the probability of A3 given A1 and A2, corresponding to the probability of A given B and C. This new equation continues, being further multiplied in a similar pattern based on how many events were being looked at in our original joint probability. We can apply this chain rule to extending the Bayes rule into a rather complex-looking equation. This approach can be potentially useful when we can't assume independence, as we'll examine more later. And this approach can also be difficult to use based on what probabilities we're able to gather in the real world ahead of time. As a quick interlude, let's also discuss some other probability terminology. The first is the term prior. This is used to describe the probability of an event alone, or in other words, the probability of that event before any other evidence was available to place it in context. The likelihood is also used to describe conditional probabilities. For example, the probability of B given A, or we could say this as assuming the outcome A, how likely is the evidence B? Then there's the term posterior. This describes the conditional probability of the outcome after knowing the evidence, which in this example is B. Note that all of these terms are relative to A, in this case being our target outcome, and B being some supporting evidence. And lastly, we have the term inference, which in this context is deriving unknown probability from known ones. Now let's move on to statistical inference. Let's start by looking at inference with the Bayes rule. Here we want to compute the probability of a query, or some outcome, but that probability is going to be conditioned on some existing evidence. So for example, in asking what the probability is that we have the outcome flu, we might want to take into consideration the evidence as to whether or not we have a headache. So imagine we have the rule, if headache, then flu. We can express this as the probability of flu given that we have a headache. And here's where the Bayes rule comes in. This is because we have a conditional probability that we want to understand and calculate. In this case, let's say that we have the following prior knowledge. We know that the prior probability of having a headache is 0.1 or 10% of people. We also know that the prior probability of having the flu is 1 in 100, or 1% of people. And let's also assume we have the following conditional probability, or the probability of having a headache given that you have a flu, which perhaps we've collected through survey information to be about 90% of people. Now we have to use the Bayes rule to calculate the probability of having the flu given that you have a headache. In this case, 0.9 comes from our conditional probability here, multiplied by the probability of having the flu alone, and this is all divided by the probability of having a headache alone, giving us a conditional probability of 0.09 or 9% of people. This tells us that if we know that someone has a headache, there's only a 9% chance that that headache indicates that you have a flu. This is a much smaller chance than the 90%, which came from the probability of having a headache given that you had the flu. But notably, it's higher than the probability of having the flu in general, which is only 1%. So in this case, the evidence that an individual had a headache raised the probability that a person had the flu from a prior probability of 1% to a new conditional probability of 9%. Now let's look at a classic example of probability inference using the Bayes rule. In this example, we have a bag with two envelopes. One envelope has a red ball, worth $100, as well as a black ball, and the other envelope just has two black balls that won't win you a prize. Let's say you're a participant in this game to win $100, and you randomly grabbed an envelope. From that envelope, you randomly took out one ball and discovered that it was black. At this point, as a player of the game trying to win $100, should you switch to the other envelope for another draw, or do you stick with the envelope you already drew a ball from? Take a moment to pause this video and see if you can get the right answer. With your answer in mind, let's walk through how to calculate the best choice in this example problem. Let's start off by defining the variables we use. The variable E is used to represent an envelope, where envelope 1 has a red ball and a black ball, and envelope 2 has two black balls. In reality, we don't know the underlying states of both envelopes, but we're just going to assign them these values for the purpose of demonstrating how this problem would work out. We also have a variable b that describes the event of drawing a black ball. We know that our prior probability of drawing a black ball is 3 out of 4, since 3 out of the 4 balls are black. We can also calculate the conditional probability of drawing a black ball from either envelope. So for example, the probability of drawing a black ball, given that we have envelope 1, is 50-50, since envelope 1 contains both a red and black ball. And the probability of drawing a black ball for envelope 2 is 100%, or 1. Also, the probability of having picked one envelope or the other is assumed to be 50-50. So the prior probability that you picked envelope 1 and the prior probability that you picked envelope 2 are both 0.5. Next, we want to work out what's the probability that you picked envelope X given that you drew a black ball. We'll write this as follows. Probability of EX given B is equal to the probability of B given EX times the probability of EX divided by the probability of B. Here we use the Bayes rule and enter values for these variables to try and calculate this probability. So next we want to calculate this for both the situation where you have envelope 1 or envelope 2 and compare them. So first, what's the probability that we drew envelope 1 given that we drew a black ball? Based on the Bayes rule, we'd calculate this to be 1/3. Differently, what's the probability we drew envelope 2 given that we drew a black ball? In this case, we would get 2/3. Therefore, the likelihood is greater that you picked envelope 2 with 2 black balls in it, given that you drew a black ball in your first attempt. This can be counterintuitive, as you might expect in your first draw that you had a 1 out of 4 chance of picking the red ball, and in your second draw, you now had a 1 out of 3 chance of picking a red ball. However, the evidence that in your first attempt you drew a black ball does alter the probabilities. Therefore, the better strategy is to switch to the other envelope and take your chances that you'll pull a red ball. Of course, this strategy is not certain. We're dealing with probabilities, but on average, this scenario, where you drew a black ball in your first attempt, your odds of picking a red ball in the second attempt are better if you switch envelopes. This example that we just walked through is very similar to the classic Monty Hall problem, where contestants aim to correctly find the prize hidden behind one of 3 doors. At the bottom of this slide are a couple of really nice videos that explain and break down the solution of this problem piece by piece. So next we might ask, why do we bother with the Bayes rule when we're building an expert system, or why do we make things this complicated? In other words, why not just calculate the probability of having the flu given that an individual has a headache from the data directly, in order to use that in an expert system we're building? Well, at the end of the day, it often comes down to the accessibility of that data. Patients that clinicians can easily observe in their clinic will usually be identified as ultimately having a given disease. Otherwise, they probably wouldn't have been in the clinic to begin with. So from these patients, we can easily get the probability of symptoms, for example, the probability of a headache given the disease flu. But it's not really practical to gather up all people with headaches and then survey how many of them have the flu. In diagnosis problems, we often have available data on probabilities of various symptoms of different diseases. For example, the prior probability of having a headache. So with these 2 kinds of probabilities, we can go ahead and calculate this original probability that we want using the Bayes rule. You might also reasonably ask, why not calculate this target probability that we're interested in using the joint probability of flu and headaches divided by the probability of headaches, rather than again using the Bayes rule? Well, the joint probability of F and H can also be difficult to gather data on. Here you'd need to build a joint probability table, which in certain problems might be possible, but it's potentially very impractical as the scale of a problem gets bigger. At the end of the day, when it comes to uncertainty, reasoning, and probabilities, you're going to want to work with the data that's most feasible to collect, as well as the data that's most reliably collected. Now let's look at a couple more slightly advanced things we can do with the Bayes rule. For example, what if we don't have available data on symptom probability, or in other words, probability of B? Well, if the occurrence of an event A depends on only 2 mutually exclusive events, B and not B, we obtain an alternative way to calculate the probability of B. Or in other words, the probability of B given A times the probability of A plus the probability of B given that we don't have A times the probability that we don't have A. We can then substitute this equation into the Bayes rule, giving us the following. So now on the dividend of this equation, the probability of B is replaced by this whole expression from above. Notably, the probability of not A is the prior probability of hypothesis A being false. So this could be the probability of not having a headache. Basically, we show this manipulation to illustrate how when some pieces of evidence or probabilities aren't available or can't be easily calculated, there are often alternative ways to calculate them based on available information. Also of note, here the probability of B given not A is the probability of finding evidence B even when hypothesis A is false. Next, let's shift gears to thinking about the impact of independence assumptions in these probability calculations. We generally start thinking about independence when we have a situation where we want to reason with multiple pieces of evidence. But before we can do this, we need to understand which bits of evidence are independent from others. As we mentioned earlier, two facts, let's say E1 and E2, are independent of each other if and only if they have no influence on each other. To put this formally, two events A and B are independent if their joint probability is the product of their individual probabilities, as we saw earlier, or the probability of A does not change given the evidence B, or in this case, the probability of A conditional on B is equivalent to just the probability of A alone. Further, the probability of B does not change given A, or the probability of B given A is also equal to the probability of B. If all three of these things are satisfied, you know that A and B are independent of one another. Whether variables are independent is in itself important domain knowledge to have on a problem. If in this example A and B are independent, then the joint probability table between them can be calculated quite simply. And this table will ultimately have k to the 2 cells, where k is the number of variables you have. Before diving into situations where independence is not satisfied, let's look at how the assumption of independence could be misused in calculating probabilities. So here we have an anecdote of a famous statistician who had never traveled by airplane because he had studied air travel and estimated that the probability of there being a bomb on any given flight was 1 in a million, and he was not prepared to accept those odds. One day, a colleague met him at a conference far from home and said, "How did you get here, by train?" And the statistician said, "No, I flew." And his colleague commented, "What about the possibility of a bomb?" And the statistician said, "Well, I began thinking that if the odds of one bomb are 1 in a million, then the odds of two bombs are 1 in a million times 1 in a million. And this is a very, very small probability which he thought he could accept. So now he brings his own bomb along." Of course, the humor in this anecdote is derived from the misuse of the independence assumption. Here, the statistician failed to recognize that there was dependency between the evidence of intending to use the bomb and the presence of a bomb. So in this story, the original odds of a bomb having been brought on the airplane remain at the original 1 in a million, despite the fact that the statistician brought his own. Now let's talk about the concept of conditional independence. Notably, random variables can be dependent, yet conditionally independent. As an example, imagine your house has an alarm, and your neighbor John will call when he hears the alarm. You also have a neighbor, Mary, that will also call when she hears the alarm. But we assume that John and Mary don't talk to each other. So in this case, is John's calling independent of Mary's calling? And the answer here is no. If John called, likely the alarm went off, which increases the probability that Mary will call. Or another way of putting this is the probability of Mary calling, given that John called, is not equal to just Mary calling alone. However, if we know the status of the alarm, then the probability of John calling shouldn't affect the probability of Mary calling at all. So in this case, the probability of Mary calling, given that the alarm sounded and that John called, is the same as the probability of Mary calling just given that the alarm sounded. So in this example, we say that John calling and Mary calling are conditionally independent, given that the alarm went off. Another way of phrasing this is that those two variables are independent, conditioned on whether the alarm went off or not. In general, A and B are conditionally independent given C if the following situations are true. The probability of A given B and C is equal to the probability of A given C. Or the probability of B given A and C is equal to the probability of B given C. Or the joint probability of A and B given C is equal to the probability of A given C times the probability of B given C. So all these equations represent situations where you can check the conditional independence between two variables. Now let's talk about how conditional independence comes into play in practice. For diagnostic tasks, we're interested in conditional independence of a collection of bits of evidence, which we'll call E1 through En here, given some hypothesis H. This assumption is often made even when the data can't be collected to confirm it, and this is for a number of practical reasons. Specifically, this allows us to dramatically simplify probabilistic reasoning by reducing the number of data we need to collect in order to calculate anything. In practice, we can use this assumption of conditional independence, where it seems appropriate, to the phenomena being modeled. But at the end of the day, we have to use our common sense and educated guessing to put forward this assumption of conditional independence. As an example, imagine we're looking at pneumonia as a hypothesis. We might expect a causal relationship between the presence of pneumonia and positive findings on a chest X-ray, as well as the presence of pneumonia and the presence of a cough. Therefore, once it's known that pneumonia is present, the probability of a positive X-ray will likely be the same whether or not a cough is present. Thus, it's reasonable here to assume that a positive X-ray and a cough are conditionally independent, given pneumonia. If we allow ourselves to assume conditional independence, or we check that it's actually true, then we can get the following for Bayes' rules. So here we have the probability of some hypothesis given a collection of bits of evidence, and we can use the Bayes' rule form to rewrite this equation to be calculated as such. First, we can write it like this, where we have the probability of jointly having all these pieces of evidence given the hypothesis, times the prior probability of the hypothesis, divided by the joint probability of all evidences. This can further be written as such, where we have the conditional probability of each piece of evidence given the hypothesis, all multiplied by one another as well, and again multiplied by the prior probability of the hypothesis. This again is divided by the joint probability of all pieces of evidence. This equation is much simpler than if we had to rely on the chain rule we learned earlier, where recall that the chain rule can be used even when we can't assume independence. But in order to use these equations, we still need to know the joint probability of all symptoms, as we can see here in the denominator. However, we can do similar manipulations of the Bayes rule if the possible hypotheses are exhaustive as well as mutually exclusive, or in other words, if everyone has one of the diseases but no more. In this situation, we can manipulate the Bayes rule to look like this, where we're trying to understand the probability of a hypothesis given these pieces of evidence as being equal to this expression. Now let's take a quick look at reasoning with multiple hypotheses. So in this case, we're trying to take into account both multiple hypotheses, let's say H1 through HM, and multiple pieces of evidence, E1 through En. Here, the hypotheses as well as all the evidences must be mutually exclusive and exhaustive. But in this case, we're back to a lack of assumption of conditional independence. First, let's look at the equation for dealing with a single piece of evidence and multiple hypotheses. Differently, we have the following equation for dealing with multiple pieces of evidence as well as multiple hypotheses. As you can see, this gets to be somewhat of a complex mess. The use of the equations on the last slide required us to obtain the conditional probabilities of all possible combinations of evidences for all hypotheses, and this can place an enormous burden on the expert or researcher that's trying to gather the data. Therefore, conditional independence among different evidences are assumed in a way that's hopefully upheld by the data, and in this case, we can use this equation, filled with a number of conditional probabilities, that generally would be easier to calculate. For example, the probability of evidence 1 given a hypothesis. This equation is what would most commonly be applied in expert systems that rely on a more formal, probabilistic framework for calculating uncertainty. Next, we're going to transition into thinking about ranking potentially true hypotheses given different bits of evidence. So let's examine this simple example where we have an expert who's given 3 conditionally independent evidences, E1, 2, and 3, and they create 3 mutually exclusive and exhaustive hypotheses, H1, H2, and H3. Furthermore, they provide prior probabilities for all of these hypotheses, in other words, the probability of H1, H2, and H3 respectively. The expert also determines the conditional probabilities of observing each evidence for all possible hypotheses. This is all captured in this table here. At the top, we have our 3 hypotheses. I is 1, I is 2, and I is 3. Along this column, we have different probabilities. At the top is the prior probability of a given hypothesis, then the probability of evidence 1 given that hypothesis, then the probability of evidence 2 given that hypothesis, and the probability of evidence 3 given that hypothesis. So for example, the probability that you'd see evidence 3 given that you have disease 3 is 90%. In this example, let's say that we first observe evidence 3, and the expert system now computes the posterior probabilities for all hypotheses. So here, we're applying the aforementioned equation, where we're assuming conditional independence, and we have 3 hypotheses for I. Therefore, we have the probability of each hypothesis given that we have evidence 3, as seen in this equation. Here are those 3 calculations, one for each of the hypotheses. Recall that before we knew any of this evidence, our prior probabilities of any one of these hypotheses outcomes are listed here in this row, with hypothesis 1 being the most likely. After calculating the conditional probabilities of these hypotheses given evidence 3, we now see that hypothesis 1 and 2 are now equally likely, and hypothesis 3 is still least likely. However, all 3 of these probabilities are now quite close to one another. Now let's suppose we get evidence 1 in addition to evidence 3. So again, we're going to calculate these posterior probabilities using this equation, now where we have 2 pieces of evidence to consider. Now we look at the updated conditional probabilities for each of the hypotheses, and find that hypothesis 2 is now much more likely than the other 2 hypotheses. Now let's say we finally get evidence 2, and we want to calculate our final posterior probabilities for all hypotheses. Again, here is our conditional probability equation for each hypothesis, given all 3 pieces of evidence. And we see the final calculated probabilities for each, where now with the introduction of evidence 2, the probability of hypothesis 2 has gone down to 0. And we find that by including all 3 pieces of evidence, that hypothesis 3 is now the most probable. This is despite hypothesis 3 originally having had the lowest probability. Now let's examine some common alternative odds likelihood forms for Bayes, aimed at simplifying these concepts for everyday clinical use. Bayes' theorem and probabilities can be awkward for people to work with in diagnostic problems. Thus, they are often reformulated using odds and likelihood ratios. Let's start by taking a moment to distinguish probabilities from odds. Odds, specified in the form O of x, are not the same thing as probabilities, given the form P of x. Odds are calculated using this equation, involving the probability that something is true divided by the probability that that same something is false. This is just like the odds on horse racing, where if the odds of a horse Speedy to win are 3 to 2, then there are 3 chances of him winning to 2 chances of him not winning. Odds of 3 to 2 or 1.5 on a disease mean that 3 people will have it for every 2 that don't. The term prior odds refers to the belief in something before seeing any additional evidentiary data. This brings us to the term likelihood ratio. This is a number that quantifies the strength of evidence provided by a test result or observation. It indicates how much more likely a specific result is to occur in one scenario, for example having a disease, compared to an alternate scenario, for example being healthy. It's calculated as the probability that a test is correct divided by the probability that it is incorrect, as seen in this equation, using odds form, and it assesses how much more likely the data is under one hypothesis versus another. As a quick side note, in a clinical or diagnostic setting, a similar form of positive and negative likelihood ratios are often used. Here, likelihood ratios are often derived from a test's sensitivity and specificity. These come in two varieties. A positive likelihood ratio, or LR+, is the probability of a positive test in someone with the disease, divided by the probability of a positive test in someone without it, otherwise known as sensitivity divided by 1 minus specificity. A high positive likelihood ratio, for example over 10, strongly suggests the disease is present. Differently, a negative likelihood ratio, or LR-, is the probability of a negative test in someone with the disease divided by the probability of a negative test in someone without it, otherwise known as 1 minus sensitivity divided by specificity. A low negative likelihood ratio, for example less than 0.1, strongly suggests the disease is absent. Let's also take a moment to look at why people use likelihood ratios. In short, they tend to be more versatile and intuitive for decision-making than other statistical metrics. For one, they have prevalence independence, meaning that unlike predictive values, likelihood ratios do not change based on the prevalence of a condition in the population. They are stable properties of the test itself that can be applied to individual patients regardless of the setting. Second, they can be mathematically updated using Bayesian reasoning. Likelihood ratios provide the simplest way to update your beliefs, and this is done by multiplying your prior odds, or starting belief, by the likelihood ratio in order to directly calculate your posterior odds, or your new belief. Third, they can be used to handle multiple test results. Likelihood ratios can be used for tests with more than 2 outcomes, or continuous numerical data. They also allow you to combine results from multiple independent tests simply by multiplying their respective likelihood ratios. And last, they offer clinical utility. Tools like the Fagan nonogram allow clinicians to bypass complex math and visually see how a test result shifts the probability of a diagnosis for a specific patient. Now let's look at calculating posterior odds, which are your updated belief after incorporating data. These are related to conditional probabilities we discussed earlier. In this equation, we have the odds of a hypothesis given evidence being equal to the probability of the hypothesis given evidence divided by 1 minus the probability of the hypothesis given evidence. Recall how we calculated this conditional probability, probability H given E, using the Bayes rule. So for example here, maybe the odds of a person having a disease is 5 to 2, given that they have fever as evidence. To update posterior odds, we can use something called level of sufficiency, or LS. LS considers how adequate some evidence E is for concluding our hypothesis. It's calculated by the following equation. As the probability of evidence given our hypothesis is true, divided by the probability of evidence given our hypothesis is not true. Going back to our discussion of the positive likelihood ratio, calculated using sensitivity and specificity, we note that both of these equations capture the same informational value, however, they are not mathematically equivalent. Next, using both LS and our prior odds, we can reformulate our posterior odds equation as follows. The odds of a hypothesis given evidence equals LS times our prior odds of the hypothesis. Both of these terms come from the equations we've already seen, as indicated by these arrows. We can also use posterior odds with multiple evidences. Again, assuming conditional independence, we can multiply together each level of sufficiency for each bit of evidence. Then we can multiply the result by the prior odds. So let's take a look at an example where here we have 2 hypotheses of either measles or mumps, and included are their LS values given pieces of evidence. You could think of these values as the odds that you'd see that evidence given that they have the target outcome. For example, here, spots are more indicative of measles than they are of mumps. Let's say that in this situation, we also know that the prior odds of having measles is 0.1 and the prior odds of having mumps is 0.05. So now, given that a patient has spots but no temperature, what are the odds of having either measles or mumps? Well, we can calculate this using that equation from our last slide, where we have the odds of measles given spots and no temperature being calculated as the LS of measles with spots times the LS of measles with no temperature, further multiplied by the prior odds of measles, giving us final odds of 1.2. We can similarly calculate this for mumps, given spots and not having a temperature, to be 0.35. So in this case, given those two pieces of evidence, spots and no temperature, we know that the probability of, or the odds of having measles is quite a bit greater. Let's now end this lecture by talking briefly about the trouble with Bayes. The framework for Bayesian reasoning requires probability values as the primary inputs. You could start with patient data to determine the likelihood ratios and prior odds of different diseases. And if data weren't available, an expert could make educated guesses. However, of course, there are many potential sources of error. For one, the symptoms may not be independent given the disease, and the likelihood ratios and prior odds may be inaccurate based on non-representative or overly small samples of patients, or just poor guesses on the part of experts. Often simple solutions that deal with uncertainty may give the illusion of precision. For example, they could output a high probability for a given outcome, such as 96%. But there could be critical errors behind these values if the system wasn't set up correctly or the assumptions that went in behind the probability calculations were not satisfied. Further, if we don't make assumptions about the conditional independence of these variables, we would need huge tables of conditional probabilities. So for example, what's the probability of each hypothesis for every single unique combination of evidence possible? Typically, doing this just isn't practical. So for example, given 16 possible symptoms, we'd need a table with 2 to the power of 16, or over 65,000 entries for every disease. It's unlikely that we would have enough data on past patients to get accurate probabilities for each. So the message here is that the performance of Bayesian statistical reasoning systems deteriorates as larger numbers of diseases and symptoms are considered, and this is primarily due to the violation of conditional independence that we've discussed. To summarize this lecture, uncertainty is a fairly ubiquitous challenge in real-world problems and can come from many sources. Important concepts involving probability include disjoint probabilities, mutually exclusive events, joint probabilities, and conditional probabilities. The Bayes rule can be applied to make statistical inferences using the chain rule when we can't assume the independence of pieces of evidence, but also much simpler forms are available that we can get away with when assuming the conditional independence of evidence. We can use these strategies to reason with multiple pieces of evidence as well as multiple hypotheses. Also, other odds likelihood forms of Bayes are also commonly used in clinical or diagnostic settings that tend to be more versatile and intuitive. However, there still can be significant practical limitations when reasoning with the Bayes theorem. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.